Okay, I meant to find in 14.5, number 1, the gradient of the function of two variables y minus x at the point 2, 1. So, let's see. I am meant to find the gradient of y minus x. Okay, so what I've written so far is kind of redundant. I've said the gradient of y minus x at 2, 1 is the gradient of y minus x. I think in the future I'm going to use less redundant notation. The gradient of y minus x at 2, 1 is, oh, hold on, no. At 2, 1, this thing right here I need to evaluate at 2, 1. What is the notation for evaluating at a point? Oh yeah, it's a vertical bar. Evaluate that at 2, comma 1. Right. This is like when you use the fundamental theorem of calculus and you say that you want to evaluate at something here and something up here. Though in the fundamental theorem of calculus, you do the expression evaluated up there minus the expression evaluated down there. If you only have things down here, that means only evaluate at this. All right. So now I've been completely redundant. The gradient of y minus x at 2, 1 is the gradient of y minus x at 2, 1, which is equal to. So I didn't even need that line at all. This right here is just shorthand for that. Okay, time to get started with the calculation then. There's various ways to write this. Let's see, I could go with the standard unit vector notation, I hat d dx plus j hat d dy. That's just one way of writing nabla. Oh, I'm sorry, this symbol right here is nabla. Some people call it del. Its real name is Nabla. I got a thing for, the truth. Anyway, the gradient symbol is shorthand for I ddx plus j d dy. And it's going to be acting on y minus x. Okay, so this time I'll go ahead and go through with the I hat, j hat notation. And don't forget, you got to evaluate this at 2, 1. Okay. This isn't going to be too hard, I think. This is distributing I hat, the derivative with respect to x of y minus x, that is negative 1. Easy schmeezy. And then j hat, the derivative with respect to y of y minus x is 1, so just that. Okay, good. And then that thing I would like to evaluate at 2, 1. Oh, but now I feel confused. See, I meant to substitute in 2 for x and 1 for y, so not quite sure what to do. I could write this as negative 1 comma positive 1, and that I meant to evaluate at 2, 1. I suppose the issue here is that I've got two components, and those two components are both constant functions, and so yeah, that's right, the gradient here is constant, and evaluating at 2, 1 means nothing. Okay, so this constant function evaluated at 2, 1 is simply, 1, 1. Okay, I am supposed to also draw the level surface that this gradient vector is normal to, so let's see. The level surfaces, maybe I'll write this in the sentence. Right, this vector and the level sets of y minus x are drawn below. So let me go ahead and draw those. Okay, the level sets of y minus x, that's a function in two variables. So The level sets are subsets of the domain. Here's the x-axis, here's the y-axis. Let's see, the level set corresponding to 0 is the solution set to the algebraic equation y minus x is equal to 0, which is, oh, maybe I should do this in color. Let's see. This blue, now it's blue and then I've recolored it, that's the level set corresponding to 0. The level set corresponding to 1, so y minus x is equal to 1. The solution set to that, well, of course, is simply this line. And y minus x equal to -1, that'd be this line. So all these parallel lines in the plane, those are the level sets corresponding to various numbers. And I am meant to draw the vector -1, 1. Let's see, what does that look like? Oh, it's supposed to be at the point 2, 1, by the way. So let me draw the point 2, 1. You go out 1, 2, and then up 1. That would put me right here. And at that point, I should draw the vector -1, 1. So -1 in that direction, and then up 1. So up 1 in, so that would put us in this direction, and that would all come together and give me this vector. Okay, so that right there is the vector -1, 1. Okay, so it is orthogonal. I'll draw that orthogonality in yet another color. What do I have here? Green. In green, I'll write this right angle. -1, 1 is orthogonal to the level set of y minus x that passes through the point. The point right here, by the way, is 2, 1. And that's as it should be, right? The gradient vectors are supposed to be orthogonal to the level sets everywhere. Notice that in this case, the vector -1, 1 is not homeless. Really, it belongs at the point 2, 1. In this case, the gradient was constant, and you could see that if I pick up this gradient vector and drop it anywhere else, say over here, I will get a vector which again is orthogonal to one of the level sets of this function. So I can pick that up and drop it anywhere and get drop it and find that my gradient vector is orthogonal to level sets. In general, the level sets are not going to be straight lines, so this will not be the case. In general, the gradient vectors will change, they will rotate as you move around in space, and we'll see that in future examples. This was a bit of an oddball, again, because the gradient vector was constant.